In the past lectures, we have been discussing perturbation theory, in particular time-independent perturbation theory in quantum mechanics. Now in all these lectures, we have essentially focused on one particular method, the Rayleigh-Schrödinger perturbation theory, often called RSPT for short. Now, most textbooks actually focus on the RSPT more than any other method. In fact, most textbooks do not even mention any other perturbation theoretic method for the time-independent Schrödinger equation. Actually, however, there are many other techniques which are available, and depending on the problem, one of those other techniques may be easier to use or may even be the only method you can use for a particular problem. Now, it is impossible to actually give a complete survey of all the methods available. So, in this lecture, what I am going to do is I am going to give you one example of a method which is used extensively in time-independent perturbation theory, which goes beyond RSPT, beyond the Rayleigh-Schrödinger perturbation theory that we have been discussing so far. And this is called the Dalgarno-Stewart method. Now, notice that in the Rayleigh-Schrödinger perturbation theory, what we do is we calculate corrections to the unperturbed energy and eigenkets. But these corrections are actually written in terms of the unperturbed eigenkets, or basically expanded in a basis formed by the unperturbed eigenkets. Now, while this is a perfectly useful method and is a very successful one, there may be situations where other methods are more convenient. For example, it may be more convenient to directly deal with the wave functions rather than a complete basis. And one of the methods, this is not the only method that does this, but one of the methods that does this is the method of Dalgarno and Stewart. That is the one we are going to discuss here. So, here we deal explicitly with a Hamiltonian in a position representation, which of course accounts for most of the Hamiltonians that we work with. And we are using special units here. H cross and m has been set equal to 1, and so the equation, the Hamiltonian comes out to be minus half times the Laplacian in 3 dimensions plus v of r. Of course, in 1 dimension this would have simply been minus half d2 dx2 plus v of x. Now, as in standard perturbation theory or RSPT, we have to assume that there is a related Hamiltonian H0 whose spectrum is exactly known, whose eigenfunctions and eigenvalues are exactly known, and this H0 is minus half Laplacian, the kinetic part, plus V0 of r, some potential which is close to the potential of the problem that we want to solve, but one for which the Schrödinger equation has been exactly solved. So we are assuming that H0 psi n0 equals En0 psi n0. This equation is exactly solved. Notice the n here in the suffix stands for the nth level, and the upper 0 in the bracket here are just for 0th order perturbation theory. Of course, in this context, these are just the eigenvalues and eigenfunctions for the operator H0. Of course, the difference between V of r and V0 of r is our perturbation, and we throw in a parameter lambda. This parameter lambda is simply there to keep track of the order of perturbation, which is familiar to all of you because we have done this in RSPT as well. So we write V of r minus V0 of r as lambda times V1 of r, and this V1 is actually our perturbation, and in the end we will put lambda equal to 1, but lambda is of course a formal parameter which we need to keep track of how many times V1 is being used. in the perturbation equation. So as in the Rayleigh-Schrodinger perturbation theory, we seek perturbative solutions for the Schrodinger equation for the full Hamiltonian. H psi n equals En psi n. And what we do is we expand En and psi n in powers of lambda. So lambda is a j, En j, the j in the bracket up here is not, let me remind you, a power. It simply indicates that this is the jth order correction. So En0, of course, was the uncorrected, unperturbed energy eigenvalue. En1, En2, En3, these will be first order, second order, third order corrections. And a similar notation also works for the wave function. The wave function psi n of r is expanded in powers of lambda, and so psi n0 of course is the unperturbed wave function. Then you have psi n1, psi n2, psi n3, these are the higher order corrections. And when you plug it into the Schrodinger equation and keep track of the powers of lambda, we get the jth order perturbation equation as we did earlier in RSPT in this form: H0 psi nj plus V1 psi nj minus 1 equals a sum over I Eni psi nj minus I. So this is something we have already done before, so I don't want to talk too much about the derivation of this. If you are confused, you can always look at the earlier lectures, or it's perhaps easier to just sit down and work it out yourself. Just plug the entire set, this expansion for En, this one for psi n, in the Schrodinger equation, remembering that H is H0 plus lambda V1, and just compare equal powers of lambda on both sides, and that will give you this equation. So far everything is very much like the RSPT, the Rayleigh-Schrodinger perturbation theory. What is the difference? Well, in the Rayleigh-Schrodinger perturbation theory, to proceed further, what we do is take overlaps with the nth wave functions, the nth order wave functions, and from that try to figure out unperturbed wave functions, and from that try to find out various corrections to the wave function and so on. In the Dalgarno-Stewart method, on the other hand, what you do is you write the jth wave function correction, psi njr, in terms of the unperturbed wave function for the nth order, the wave function for to which you are seeking the correction, into a function fj of r, and try to find out this function fj. But that may not look like a very big difference, but sometimes it makes the problem much more tractable, or at least gives you the answer you are seeking much more quickly. So how does one go about doing this? Before we describe the calculation in detail, let us simplify the notation a bit. There really are a lot of indices in what we talked about before. So let me just simplify this a bit. Since we are always going to talk about one particular unperturbed level, the nth one, let us not mention the n index any longer, and rather than have an awkward looking superfix, which people may confuse with a power, let's move this superfix down here to an index. So what we are going to call psi j now is a jth order correction to the nth order unperturbed wave function. The nth order is going to be omitted from the notation. So of course psi n0, which was the unperturbed nth order wave function, becomes psi 0 in this notation. Let me warn you that here psi 0 does not necessarily mean the ground state wave function. So that's a possible confusion. So I'm alerting you to that at this stage. Psi 0 stands for whatever unperturbed wave function it is to which you are seeking a correction. So could be the ground state, could be the first excited, could be the second excited, whatever. And of course Enj in this notation simply becomes Ej. So our perturbation equation, the jth order perturbation equation, simplifies a bit. At least the equation stays the same. It looks a bit simpler because we have dropped a lot of the extra indices. So H0 psi j plus V1 psi j minus 1 is equal to sum over I going from 0 to j, ei psi j minus I. Notice that this sum really reflects the fact that each ei comes with lambda to the I and each psi j minus I comes with lambda to the j minus I. So they together give you the power j for lambda, and you collect all such terms together on this side. And the answers that we used for the jth order correction in this notation simply becomes psi j equals fj psi 0. Once again, if we remind you, the psi 0 here does not necessarily mean the ground state wave function. It means the unperturbed wave function, whatever state you're talking about. So now, let's start with this equation and try to use the fact that H0 is known and well understood to simplify this a bit further and write down an equation for f. So what is H0 psi j? Remember, H0 is simply minus half Laplacian plus V0 of R. This whole thing acting on fj psi 0, the product. Now this is pretty straightforward. You need to know how to apply the Laplacian on a product of two functions, and the Laplacian on a product is simply this fj acting on the Laplacian plus psi 0 times Laplacian acting on fj plus an extra term which essentially is like the twice AB term, the twice grad fj dot grad psi 0. Of course, if this had been in one dimension, what you would have needed is the second derivative of the product fj psi 0, and then this would simply have been the Leibniz rule for successive differentiation, fj d2 psi 0 dx2 plus twice dfj dx times d psi 0 dx plus psi 0 d2 fj dx2. Here the final result is very similar, except for d2 dx2 you have the Laplacian, except for the first derivatives you have the gradients and the dot product of the gradients. Now all I need to do is plug this whole thing H0 psi j, this expression for Laplacian in H0 psi j, and if you put them in, so if you take this Laplacian expression here and plug it into H0 psi j, it simply becomes this term here. Notice that despite looking rather complicated, this is really this one term from the Laplacian of the product multiplied by, and to which you are adding the V0R terms of j psi 0. So that gives you this term here. The other two terms here are simply minus half times these two terms. But what is important is the minus half Laplacian V0R acting on psi 0, of course, gives you E0 psi 0. So E0 psi 0 times fj V0 psi j. So that's all we have done here. So what we do is take this expression for H0 psi j and plug it back in our perturbation equation. So we get E0 psi j. So these terms, all of these three terms are basically H0 psi j plus V1 fj minus 1 psi 0. That's nothing but V1 psi j minus 1. And what is that equal to? On the other side, this is a sum from I equals 0 to j, but I deliberately split this into the I equal to 0 term and the rest of the terms from I equal to 1 to j of the rest. Why have I done that? Because E0 psi j is already there on the left hand side. So splitting this up this way means the E0 psi j will just cancel. So this is what you are left with. After you divide that equation by the psi 0 which is there in every term, and minus half Laplacian fj minus 1 by psi 0 grad psi 0 dot grad fj plus V1 fj minus 1 minus sum over I equal to 1 to j ei fj minus I, and this whole thing has to be equal to 0. This is in 3 dimensions. The one dimensional version simply replaces all these Laplacians by derivatives, so you get fj double prime. This grad psi 0 by psi 0 becomes psi 0 prime by psi 0. which remember is the derivative of the log of psi 0. This one of course also is the gradient of the log of psi 0, fj prime, and so on. So this is the basic equation for the Dalgarno-Stewart method. Now it might seem to you that what we have done is we have taken something which was reasonably simple to begin with, the Rayleigh-Schrodinger perturbation theory, and replace it by a much more complicated thing. The fj factor which we now have to determine is now a solution of a second order differential equation for 1D in the 1D case, and a second order partial differential equation in the 3D case. So it looks much more complicated than what we started out with. But it so transpires that for most situations, this actually is easier to handle than the original Schrodinger equation. Of course, there are infinitely many of them, one for every value of j, starting from 1, 2, 3 and so on. But as in all perturbation theory, we are only going to work out the lower few terms. And actually it so happens that we can systematically write computer programs to calculate the results of higher and higher order terms without much difficulty, but we will not go there in this lecture. Now, let me just point out that the reason why this is really not as complicated as the Schrodinger equation, despite looking more complicated, is the fact that the Schrodinger equation is an eigenvalue equation. The eigenvalue E is not known beforehand, and basically you have to finally decide on what the eigenvalue E has to be based on boundary conditions which the wave function has to satisfy. In this case, the functions fj are really multiplying factors over and above psi 0. So job of the boundary condition is essential, that is the thing, the wave function vanishing at infinity and all that is taken care of by psi 0 itself. So we have to focus essentially on fj and not worry too much about the boundary conditions. Also, notice that at any given order j, Ej does appear, but all other terms, all other E's are actually of lower order, which means by the time you have got to j, you have already calculated them. But okay, let me just give you an example which should convince you that this is really not that difficult to use, rather than say a lot of things which may not make very much sense to you right now. So let's go on to a particular example. We are going to go back to an example which we have seen before, the quartic perturbation on top of a simple harmonic oscillator. So my Hamiltonian, again in units h cross equals m equals 1 and omega equals 1 as well, is simply this minus half d2 dx2 plus half x squared. This is h0. To that there is this quartic anharmonic term lambda x over 4. So that's our setup. And let's say we are trying to calculate the corrections to the ground state wave function. Now the results of course will be the same as those obtained by Rayleigh-Schrodinger perturbation theory. The approach to the results will be different. So let me try to explain that to you. Of course, we already know the ground state. The normalized ground state is given here. But frankly, for most of the work, you will not need the normalization that much. You will need this behavior, e to the power minus half x square. And let me remind you, this is the equation that you have. Well, this was not exactly the equation that you had earlier. Earlier you had psi 0 prime by psi 0 here, minus psi 0 prime by psi 0 here, actually to be precise, and v1 here. v1 of course is x of 4. v1, remember, is the perturbation is lambda v1, so v1 is just x of 4, which is sitting here. And because of this very simple form of the wave function psi 0 prime by psi 0, which is a derivative of log of psi 0, is simply minus x, and because of the minus sign which was already there in the equation, you end up with plus x. So this is your perturbation equation for the jth order. Right. Now let us look at what happens when j is equal to 1. For j equals 1, of course this sum has only one term. Sorry, there is a typo here. This should be minus E1, the first order energy correction. So minus E1 times F0. By the way, F0 is 1 because the zeroth order wave function, of course, is psi 0 itself. So remember, psi j is Fj psi 0. Psi 0 is, of course, F0 psi 0. So F0 is 1. Okay. So this is just minus E1 here. I've missed the 1 somehow. And this equation simply becomes minus half F1 double prime plus x F1 prime plus x to the 4 into F0, which is 1, as I said, minus E1. And this is equal to 0. Now this is a differential equation I have to solve. Now, as I said before, this looks like a pretty complicated differential equation to solve. And it might look like we have essentially a much more difficult task at hand than just solving the Schrodinger equation originally. After all, just solving this one equation will not do. You have to solve it for j equals 2, j equals 3 and so on. Now, let me point out one thing. This solution, or rather this equation, actually is guaranteed to have polynomial solutions of degree 4. How do we know that? Because if I start with a polynomial of degree 4, this becomes a polynomial of degree 2. This stays a polynomial of degree 4. So these two terms combined is a polynomial of degree 4. And all you have to do is choose the coefficients cleverly so that they cancel out whatever you have here. And you end up with a 0. Is that the only solution? Of course not. But what are the other solutions? The other solutions can be figured out from the behavior of this equation very far away. In fact, not the other solutions, but at least the behavior at x, as for very large values of x, can be easily figured out. And you can easily show that for very large x, these solutions diverge, and diverge exponentially, in fact, diverge like e to the power x square. Now, if you remember your derivation or your work for the harmonic oscillator, you should remember that the differential equation that you obtained for the harmonic oscillator actually had singularities, essential singularities at x equal to plus minus infinity. One of those essentially singular solutions there was like e to the minus x square by 2, which is the nice solution that we wanted. The other one, again essentially singular, was e to the plus x square by 2. Since this ultimately is the same equation with an added correction term, we expect the problem of having a e to the plus x square by 2 type solution to show up here as well. It does. If you do not take a polynomial solution but go in for an infinite series solution, it's going to simply blow up and give you a function which grows so fast exponentially that even with the psi 0 multiplying it, it's still going to diverge and give you a wave function which is not an admissible wave function. So keeping that in mind, what we want to do is look at a polynomial solution for f1, and as I already argued, this should have a fourth order polynomial solution. In fact, it's also easy to see that this should be an even polynomial, where after all, if you start with an even polynomial, the second derivative is still even. The first derivative is odd but is multiplied by x, so that is again even. So this will stay even, which will allow it to cancel another even polynomial. The odd part of the polynomial, if any, will have to be 0 because the odd part stays odd here and there is no odd polynomial on this side. So what we do is start with this even polynomial of degree 4, c0 plus c2x square plus c4x to the 4, where c0, c2 and c4 are coefficients that we need to find out. And all we do is just plug this back in the equation. Of course, the second derivative gives you twice c2 plus 12 c4x square with the minus half in front. This is what you get from that. Of course, x times f1 prime gives you this, and x of 4 minus e1 is 0. So this is the equation. And how do you ensure that this equation is satisfied? All you have to do is match the similar powers of x. So if you look at the x of 4 coefficient, you get 4c4 plus 1 equals 0. If you look at the x square coefficient, you get minus 6c4 plus 2c2 equals 0. And you look at x to 0 coefficient, you got minus C2 minus E1 equals 0. And these equations are actually very, very easy to solve. The first one gives you C4 equals minus 1/4, and you can use that and the second to get C2 equals 3C4, so that's minus 3/4, and E1 equals minus C2, that's plus 3/4. So you're done. That is, first order correction is done. Not only is the first order correction of energy E1 or only has that been found out, you have also found out F1x, except for one thing. As with the Rayleigh-Schrodinger perturbation theory, C0, the part of the first order correction which is in the direction of the unperturbed wave function, cannot be determined from the perturbation equation. Notice that the equation itself, once you do the second derivatives here and the first derivatives here, the C0 drops out entirely, and so there's no way you can find out C0 from this equation. So this is what your F1x is, with some C0. Now, you can fix the C0 by imposing intermediate normalization or many other ways, or you can simply ignore it. As we argued for Rayleigh-Schrodinger perturbation theory as well, the fact that perturbation theory does not tell you what C0 is does not make a difference for physical calculations. However, for many applications, it's best to have a full-blown first order correction rather than an undetermined constant. Also, if you want to use the 2s plus 1 rule, you need the wave functions to be normalized. So if you insist on normalization, we saw this before, that normalization insists that psi0, psi1, this inner product, plus its complex conjugate has to be 0. So the real part of psi0, psi1 will have to be 0. And you can use this to determine C0 pretty easily. This gives C0 is 9/16. And hence, this is my first order wave function correction. 1/4 root of pi e to the minus half x squared. This was the psi0, the unperturbed wave function. The first order wave function correction term is actually that times this fourth order polynomial. I would urge you to check that you can get the same result from the Rayleigh-Schrodinger perturbation theory as well, but in RSPT you will have to find out all the coefficients phi m psi1 overlaps, and from that reconstruct the wave function. This gives you the wave function directly. And the first order energy correction, as we have already found out, is 3/4 in these special units. Now what about the second order correction? Well, remember this was the equation that we had for arbitrary order, exactly for the harmonic oscillator potential and so on. And now let's try the j equals 2 case. Of course, j equals 2 will be, this will be f2 double prime, this will be f2 prime, this will be f1, there will be minus e1 f1 term here, and minus e2 f0, f0 of course is 1. So this is what, after you put in j equals 2, this is what the equation will look like. Okay. Now, f1 we know already is a fourth order polynomial. So this thing here is an 8th order polynomial. This whole thing, which is independent of f2, this whole expression is an 8th order polynomial, 8th order even polynomial. And using the same kind of arguments that we had used before, we can take f2 to be an 8th order even polynomial and just find out the coefficients that will match. So if you do this, plug in this function f2 in the equation, you of course get minus half times the second derivative, that's twice d2 plus 12 d2 x d4, so 2d2 coming from this, then 12 d4 x square coming from this, then 30 d6 x to the 4 coming from this, and 56 d8 x to the 6 coming from this. So that gives you the second derivative term. X f2 prime simply gives you this expression, again a very simple calculation, and of course here you have x to the 4 minus e1, which I already know is 3/4, times f1. And what I've deliberately done here, just to illustrate that not knowing C0 will really not make a difference to higher order physical results, I have not used normalization. I've kept C0 undetermined. The rest, of course, was determined from the first order perturbation theory to be this. And then you finally have a minus E2. And again, all you have to do is match the coefficients. For example, the highest power of x here is x to the 8, and there's one 8d8 here, and one term which comes from the product of these two. So x to the 4 and minus 1 by 4, x to the 4. So that gives me the equation 8d8 minus 1/4 equals 0. Next, we have x to the 6. Of course, we have x to the 6 from here, that's minus 28d8. And another x to the 6 from here, 6d6. And the other x to the 6 that we have is the product of these two terms. And that gives me this equation. Similarly, we can find out the equation which I get by matching coefficients of x to the 4, x to the 2, and x to the 0 finally. Notice that the unknown coefficient C0 is sticking here in this equation as well as in the equation for E2. So this looks like a bit of a problem because C0 cannot be, as we said, determined from the perturbation theory, and this looks like the second order energy correction will have a C0 stuck in it. But if you start solving these equations starting from the very beginning, d8 is 1 by 32, then the next equation can be solved for d6. Pretty straightforward. You can just do the simple arithmetic in your head even. The next equation will give you d4, but now d4 will have this undetermined C0 stuck in it. The next equation will give you d2 in terms of d4, but that of course will still have C0 stuck in it. But notice the d2 comes out to be of this particular form, which means E2, which is d2, which is minus d2, minus d4 C0, will simply be given by minus 21 by 8. Notice that the lack of knowledge of C0 did not prevent us from calculating E2. And finally, let me remind you that I could have obtained E2 and even E3 without actually going on to a second order perturbation calculation. I could have used the fact that I know psi0 here and psi1, which is normalized here, which is okay, psi1 is not normalized, but this ensures that psi0 plus lambda psi1, this meaning the value 9 by 16 for C0, ensures that psi0 plus lambda psi1 is normalized to first order in lambda. And with this, we also had the 2s plus 1 rule, which said that if I knew psi0 and psi1 up to psi1, psi2, psi3 up to psi-s, I should be able to use just that knowledge to find energy corrections up to order 2s plus 1. In this case, up to order 3. And just to remind you, these were results we had derived before. E2, the second order energy correction, is given by this. So now that we know psi0, we know psi1, we know x to 4 of course. This is a matter of simple integration and ultimately a simple Gaussian integral, and you can easily do the calculation and end up with the same result, minus 21 by 8 that we had obtained a while ago. And E3 is simply given by this. I do not, repeat, do not have to find out the second order energy eigenfunction for this and use that in the j equal to 3 equation. The 2s plus 1 rule allows you to find out E3 just from knowledge of psi1, and this is what you have. Again, this should be E1 here. Sorry for the typo. And this gives you 333 by 16. And that is a result which we had obtained earlier using Rayleigh-Schrodinger perturbation theory as well. Now, I would urge you to carry out the calculation to at least one more order and try to do the third order Rayleigh-Schrodinger perturbation theory calculation for the same problem in order to get an idea about which one is more useful or simpler to use and so on. There are many other methods and techniques, and why they are important is not only because they are useful in quantum mechanics, but because these techniques can be used in almost all branches of physics and mathematics, simply because there are many situations where the actual problems you have to solve are very similar to, but not the same, as problems you can solve exactly. So perturbation theoretical techniques are useful everywhere, and the things that we learn in quantum mechanics can often be translated with minimal changes to other situations as well. Now, while I could keep on describing to you other time-independent perturbation theoretic techniques, I believe the time has come to put an end to this discussion for the time being and to move on to time-dependent perturbation theory, which will be the topic of my next lecture. Bye for now.